How's it going, everybody? I know that a lot of you had some questions regarding this question. So I thought I would go through it with you. Hopefully this will help you kind of pave your way through some of these questions that are related or look like this. We've got a 0.18 molar solution of a sodium salt of nicotinic acid. Has a pH of 9.05. What is the value of the Ka for this acid? So we've got to figure out what is the Ka for nicotinic acid. You've got to be careful because the 0.18 molar is not the concentration, the initial concentration like we were used to for nicotinic acid. Notice it's for the sodium salt of nicotinic acid. So I think the first step in this journey is to understand what on heaven and earth that is, right? Because that's what the 0.18 molar obviously relates to. So to do that, we just simply have to understand that this, let's say this is nicotinic acid. I don't feel like calling it much of anything else, so I'll even put it in a cloud. There. This is nicotinic acid. So if this is nicotinic acid, then if we pair the conjugate base, which of course is that, with sodium, that would be the sodium salt of what nicotinic acid is. You thought I went somewhere, right? No, I'm just kidding. All right, so now that we understand that, I'll try to put this in plain English. When we do these questions, right, this has a pH, the sodium salt, right, has a pH of 9.05. So that obviously tells us that this thing is basic. And if there's basic, that means there's hydroxides there, and you all kind of know where we're going with this. So if you think about the ideas that we learned in class on Monday, then what we can do is take this sodium salt of nicotinic acid and think about how each of the ions, when dissociated, interacts with water. Right? So obviously this guy will not have any interactions with water because its conjugate, well, would be sodium hydroxide, and we know that's a funny joke. That's not going to happen. So it's really this guy in question. It's your conjugate base that's going to be the reason why this solution is basic anyway. So without further ado, when we look at this, this is the interaction with our conjugate base with water, and this is how we can demonstrate that this solution is indeed basic, because this is nicotinic acid, which we know is a weak acid. It's not on the strong acid list. And so this must be the reason why our solution is basic. So to help us solve this, let's go through and do our ICE table. So now we can start filling in with the data that we know. We have here 0.18 molar solution of our sodium salt. Now, yes, that does mean that our 0.18 molar solution of our sodium salt, which we said was that's the 0.18 molar. But have no fear, because a 1-to-1 mole ratio is here, right? So as you can see, 0.18 molar sodium nicotinate is technically the name of this. That's the same thing as saying 0.18 molar, right? If that's a 0.18 molar, then your sodium ions are in 0.18 molar, but so is your conjugate base. It also has to be 0.18 molar. Remember, this is a strong electrolyte. It will fully break apart in solution, and so we have a 1-to-1 mole ratio there, and we get 0.18 molar. On the video, that probably doesn't look much like an A. Let me just fix that. Much of it. So now that we understand that, we can go through and do everything else. We obviously don't care anything about water here. It's not a part of the equilibrium. And initially, right, if we take the sodium salt, and whatever amount it was, and we put it in the volume of water, these are going to be zero, at least we would expect those to be zero. And you all know how this works. This goes down by some amount as this reaction extends toward equilibrium, and these go up stoichiometrically by the same amount. That means then at equilibrium, our final concentration for our conjugate base is 0.18 minus x, and obviously these two here are x. Now the whole trick to this question comes from piecing together all the little components. Well, notice that we have a pH, which is 9.05. Now pH is obviously related to the concentration of H+, but that is not here. But we do have, well, that guy. We have OH. And if we know pH, we can get to OH pretty easily, right? So if that's our pH, if that's 9.05, then our pOH has to be 14 minus 9.05. So if you do the math there, squint 3 times, you should get a value roughly around 4.95. Now that we know our pOH, then we can use this value to help us solve the question, what is the concentration of hydroxide? So, the concentration of a hydroxide at equilibrium has to be 10 to the negative 4.95, just like we learned. And so, plugging that through your calculator, I'll be right back. It's 1.122 times 10 to the negative 5th mole. So that's got to be the concentration of hydroxide in solution, which that's exact, or at equilibrium, which that's got to be what that guy is. So the big question then becomes, okay, this, I mean, y'all know what we're about to do. We're going to take this and we can figure out, because remember, what are we looking for? We're looking for the value of the Ka. Now, when I go to write the equilibrium for this, which we understand is going to be x squared over 0.18 minus x, well, yeah, that's all great. We can plug in this value because hopefully you can connect that this has to be x. So we can plug that value in and all is fair, well, and good in the world. The big question is, what on heaven is this thing? Is this Ka? Is this the guy that we're looking for? Well, if you look at this, hopefully you will recognize this is not, well, the acid dissociation, the acid ionization. This is a base ionization. So what do we get to label the K for this thing? This has got to be Kb. Base. So, understanding that, we will find Kb from plugging in that value. That's it. So let's plug that value in. So I'm going to plug in 1.122 times 10 to the minus 5th squared. Divide that by 0.18 minus 1.122 times 10 to the minus 5th. And that gives us our Kb, which is, of course, .994 times 10 to the negative 10. So again, that's our Kb. And then remember, if we know our Kb, then we can use that very easily to figure out our Ka, because Ka times Kb is always Kw. And assuming that this is at 25 degrees Celsius, we know Kw, which is 1.00 times 10 to the negative 14. We know Kb, and therefore we can find Ka. So your Ka which is, of course, 1.00 times 10 to the minus 14 divided by 6.994 times 10 to the minus 10, and you will get 1.43 times 10 to the minus 5. And that's your Ka. So, to recap this question, all we had to do is connect the fact that this reaction right here is what will govern this question. If you can figure out what this reaction is, obviously it has to be the conjugate base reacting with water, because remember, that's what we have here. We don't actually have nicotinic acid at play. We have the sodium salt of nicotinic acid. And so why is this basic? It's basic because of this reaction. And so this is the reaction we want to use in our setup for this question. I know there's a lot written on this board, but once you get to here, this is basically just navigating through the waters of math, right? We have our ice table. We know pH, we can read OH, and so from pH we can get the concentration of hydroxide. We understand that's at equilibrium. We can find our equilibrium constant, and then you just need to remember that that's a Kb, at least in this case, in this problem. So because it's a Kb, then we can figure out our Ka from there. And in the words of Porky Pig, well, that's all, folks.